Welcome back, everyone. Ready to dive into some more fascinating math?
Always. What are we looking at today?
Well, today I thought we could explore something called the error function.
Ah, yes, the error function, or ERF, the
Yeah.
classic.
Right, ERF. And of course, we can't forget its close relative, the complementary error function.
Of course, erfc. They really go hand in hand.
They do. So maybe we should start with, well, what is the error function all about?
In essence, it helps us figure out probabilities, specifically the probability of something landing within a certain range.
Okay, so let's say we're talking about, I don't know, the heights of people.
Perfect example. You see, when you measure lots of people's heights, they tend to form that bell curve shape.
The bell curve, right, where most people are clustered around the average height.
Exactly. And the error function lets us calculate the probability of finding someone within a specific height range on that curve.
So if I wanted to know the chances of someone being between, say, 5'10" and 6'2", the error function could tell me.
Precisely. It's all about figuring out the area under that curve between those two heights.
Oh, I see. So it's like the bigger that area, the higher the probability.
You got it. Now, the actual calculation involves an integral, but visually, it's like shading in a section of that bell curve.
Okay, that makes it a bit easier to picture. So it's not just numbers, it's tied to that visual representation of the bell curve.
Absolutely. And one of the interesting things about the error function is its symmetry. It's what we call an odd function.
An odd function, does that mean it behaves weirdly?
Not weird, just special. It means that if you plug in a negative value for x, you get the negative of the result you'd get with the positive value.
So ERF of, let's say, -2 would be the negative of ERF of +2.
You got it. And visually, this means the bell curve is symmetrical. The probabilities on either side of the average mirror each other.
That's pretty cool. And it probably helps simplify things when you're working with it.
Definitely. Now, things get even more interesting when we look at what happens as we move further away from the center of that bell curve.
Okay, like towards those edges, those tails of the distribution.
Exactly. The further out we go, the smaller the probabilities become, right? That's where the limits of the error function come into play.
So as you go further out, the chances of finding something way out there get really tiny.
Exactly. As x, our distance from the center, goes towards infinity, the error function approaches 1. And as x approaches negative infinity, it goes towards -1.
So it basically captures the idea that those extreme events are really unlikely.
Precisely. But now, think about what happens right at the center of the bell curve, at the average. What do you think the error function equals there?
Well, at the average, that's where most things cluster, right? So shouldn't the probability be pretty high?
It's tempting to think that, but consider this. We're talking about the probability at a single point, an infinitely small point.
Ah, okay, so even though it's at the peak, it's still just a single point on the curve.
Right. And the probability of something landing exactly on that one infinitesimally small point is...
Well, incredibly small. Practically zero, I guess.
Exactly. And that's precisely what the error function tells us. ERF of 0 is 0. It perfectly reflects that idea of probability at a single point.
Wow, that's really neat how it ties everything together. So the error function tells us about the probability inside a certain range, but what if we want to know the probability of being outside that range?
That, my friend, is where the complementary error function steps in.
Perfect, right, the one we mentioned at the beginning. And it complements the error function. What does that even mean?
It means they work together to cover all the bases. If the error function tells you the probability of being within a certain range, the complementary error function gives you the probability of being outside of it.
Ah, I see. So if one is about what's inside, the other is about what's in those tails of the distribution.
Precisely. They're two sides of the same coin, always adding up to 1 to represent the total probability.
Okay, that makes sense. So they're like a dynamic duo working together to give us a complete picture.
You could say that. And just like with the error function, the complementary error function has some interesting properties, especially when we look at those tails of the distribution.
Oh, this is getting even more interesting. Tell me more about those properties. So those properties are erfc, the complementary error function.
Yeah.
What happens as we head out to those tails of the distribution?
Well, it kind of does the opposite of the error function. Remember, it's all about the probability outside the range. As you go further out on those tails, the probability of finding something there gets smaller and smaller.
Right, because the chances of being way out there become pretty tiny, right? So as x, the distance from the center, gets really big, erfc gets really small.
Exactly. As x approaches infinity, erfc gets closer and closer to 0.
So it's like saying the further you go out, the less likely you are to find anything.
That's a great way to put it. And it makes sense when you think about how those probabilities shrink as you move away from the center of the bell curve.
Okay, I'm with you.
Yeah.
But what about on the other side? When x approaches negative infinity, what happens to erfc then?
Think about it this way. Negative infinity just means we're going infinitely far to the left on that bell curve. The probability of being that far out there is still going to be incredibly small.
Ah, got it. So whether we go infinitely far to the right or left, erfc approaches 0.
You got it. So now let's look at a specific point. What do you think the complementary error function of 0, or erfc arrow, would be?
erfc. Okay, so we're right at the center of the bell curve. And erfc is about the probability outside the range, right?
That's right.
Well, at the center, that's where most of the probability is concentrated. So I'd guess erfc 0 would be pretty small, maybe like 0.1 or 0.2.
It's actually even more extreme than that. erfc 0 is equal to 1.
Wait, 1? But why would it be 1 at the center where the most probability is?
Remember, erfc is all about the probability outside the range. When x is 0, we're basically saying our range is just that single tiny point right at the center of the curve.
Oh, so the entire probability is outside that one infinitely small point.
Exactly. So erfc being 1 makes perfect sense. It captures the entirety of the probability distribution except for that one point.
Wow. Okay, that's pretty mind-blowing. So erf and erc really work together to cover all the probabilities inside and outside the range.
They do. They're like a perfectly balanced team.
This is all fascinating, but it feels a bit abstract. Where does all this actually show up in the real world?
Oh, these functions are everywhere. You might not see them, but they're working behind the scenes in all sorts of fields. Take heat conduction, for example.
Heat conduction, you mean like how a hot cup of coffee cools down?
Exactly. The error function can be used to describe how the temperature changes over time and distance from the heat source.
So like the hottest point would be at the center, and then it cools down as you move away, kind of like that bell curve shape.
You got it. And the error function could help us calculate things like how quickly the temperature drops at a certain distance, or how long it takes for something to reach a specific temperature.
That's incredible. I never would have connected these functions to something like heat.
And they don't stop there. They're also essential in signal processing.
Signal processing. Are we talking like in our phones and computers and stuff?
Exactly. Whenever you send a signal, there's always a chance for errors to sneak in. The complementary error function helps engineers figure out the probability of those errors, which is crucial for designing reliable communication systems.
So every time I make a call or send a text, these functions are helping to make sure my message gets through.
You could say that. They're playing a big role in ensuring our digital world runs smoothly.
It's mind-boggling to think these functions are involved in so many things. We've gone from probability on a bell curve to heat and now digital communication. Is there anything they don't do?
Well, they're not magic, but they are incredibly versatile.
Okay, so we've talked about what they are and where they're used, but how do we actually calculate them? It seems like it would involve some pretty intense math with those integrals and all.
That's where computers come in. They use some very clever techniques to approximate the values of these functions with incredible accuracy.
So we don't have to be calculus geniuses to work with them.
Not at all. Programming languages like Python and software like MATLAB have built-in functions for erf and erfc.
So they're actually quite accessible for anyone to use.
Absolutely. Modern computing power has made these complex mathematical tools much easier to work with.
That's a relief. So it seems like even without being math experts, we can understand and appreciate the impact of these functions on our lives. That's good to know. It's kind of like, we don't need to understand all the complexities of how a bridge is built to know that it's safe to drive on.
That's a great analogy. But you bring up a good point. These functions, they're really designed for situations where the data fits that bell curve shape, right? What about when we're dealing with data that's, well, a bit messier?
Right. What if it doesn't follow that nice, neat bell curve?
Well, in those cases, you'd need to use different statistical tools. The error function and its complement are specifically for the normal distribution.
So it's like you wouldn't use a hammer to tighten a screw, right? You need the right tool for the job.
Exactly. There are lots of other functions and techniques that statisticians use for different types of data.
That makes sense. But even if we don't use these specific functions every day, just understanding them gives us a better appreciation for probability and how it works, right?
Absolutely. It's like learning a new language. Once you grasp the basics, you start to see things in a different way, make connections you might not have before.
I like that. So, for someone who's intrigued and wants to learn more, where should they even start? Are we talking like advanced math textbooks and stuff?
Not necessarily. There are actually tons of resources online that explain these concepts in a pretty accessible way. Just search for error function or complementary error function, and you'll find articles, tutorials, even interactive visualizations.
So it's not just for, math whizzes. Anyone can explore this stuff if they're curious.
Exactly. And who knows, maybe it'll even spark a love of math.
Well, you certainly sparked my curiosity. I have to admit, I thought this was going to be a pretty dry topic, but you made it surprisingly interesting.
That's the thing about math. There's always something fascinating to uncover, even in those seemingly complex concepts.
I think the big takeaway here is that math isn't just about memorizing formulas. It's a way of understanding the world around us.
Couldn't agree more. And the error function and its complement, they really exemplify that. They take this abstract idea of probability and turn it into something that's used in so many practical applications.
Definitely. So to wrap things up, what's the one thing you'd want our listeners to remember from today's discussion?
I'd say, even if the math itself seems a bit daunting, the underlying ideas are often quite simple and elegant. And by understanding those ideas, you can gain a whole new perspective on the world.
Well said. And on that note, we'll leave you with a little challenge. Now that you know about the error function and the complementary error function, see if you can spot them in action in your own life. Maybe it's the probability of your commute taking a certain amount of time, or the chances of winning a game. Keep your eyes peeled, stay curious, because math is everywhere.
Until next time.